choose a sample point. Now what do I mean by sample point? So in each of the interval, for example, previously we chose left end point, then we chose right end point, we could choose middle point, okay? So we have to kind of choose the sample points actually, okay? So if I am choosing the right end points from each, what do you call, subinterval, then my sample points are these right end points. But these sample endpoints can be also left endpoints of each subinterval. The sample endpoints can be also the middle of, what do you call, each interval. Okay, so you know there are also there are all sort of, what do you call, things in there are all sort of choices actually. So let's say x naught star or x1 star, x1 star, x2 star, so on and so forth, and xn star be sample points. So what are these? These are sample points, which could be left, right, middle, okay, or any that you like actually, okay, but you have to be consistent. So instead of middle, for example, you decide to take, say, the point that is the 1/3. So for example, on each subinterval you don't want to choose the middle, but you want to choose, for example, a point that is at the 1/3 in each subinterval, at 1/3. So it doesn't matter what you choose. So these are the sample points x1 taken from subintervals x naught to x1 up to xn minus 1 to xn respectively. Okay, respectively. Then calculate the value, the height of the function at each of the sample points I, okay, and multiply it with, what do you call, the size of the subinterval delta x. Okay, so in each subinterval I choose the sample points and created a rectangle of that height, for example. So if I'm choosing middle, so I created, so my sample point is middle, and I created the height. So if this is like my x1 star actually. So this is my x1 star. So this is f of x1 star. Okay, so I choose this sample point and multiply it with the width of it. So this is going to give me the area of rectangles. So split this region into such rectangle, areas of rectangle that goes from, say, 1 to, what do you call, n. Okay, then I know that this is going to give me the area under this curve. Okay, so this sum is going to give me the area, okay, this area A under this curve actually. Now let me give this sum a name, a strange name actually. Okay, so this is a sum, so let's take a big S. So this is a big S. So I am summing, so this integral sign, or this, you can treat it as a big S. So I am summing from where to where? A to B. Okay, A to B, I'm summing from A to B. So this is a sum from A to B of what? Of the areas of the rectangle. So what is the area of rectangle? So f of x is the height of it. F of x is the height of each rectangle multiplied by dx, where the dx is the width, really tiny width of the rectangle actually. Okay? The width of the rectangle. I missed one thing. Take sum that goes from I equal to 1 to n f of xi star times delta x and take the limit n goes to infinity. So you need to take the limit actually. Okay? And I'm giving this guy a name. So this is a name of such a sum. Okay? Of the areas of rectangle. So this f of dx is representing what? So f of x is really the height. Okay, so if you take, for example, so if this is, for example, a point x, so this is f of x. Okay? And at this height, I am creating a really tiny rectangle whose width is a dx. So we know that dx is a really small quantity. And then create what do you call a rectangle. So this is a really tiny, so it looks like a big one, but it's not the big one. It's a really tiny rectangle actually. So this is representing what f of dx is representing what? So f of x is height, dx is what do you call the rectangle, and I am, so this is the area of the rectangle actually. And I am doing what? I am summing the areas of, so I am summing the areas of all such rectangles from A to B. From the end point A to B. And how can I calculate this area? This is the recipe of calculating it actually. So calculate this sum and take limit n goes to infinity. So you're going to get what do you call the value of this this new notation actually. I call this notation, okay? So I'm giving it a name actually. So this new notation is a definite integral. Okay? It's a definite integral of f, okay, of f on or from A to B. Okay? So how do I read this? So this is the definite integral of f from A to B. Okay? And for A I have a name that this is lower limit of this definite integral, and B is upper limit of the definite integral. Okay? And this f of x, I'm giving it a name. This is called the integrand. Okay? The name of this f of x is integrand. So I'm integrating, I'm summing, what do you call this integrand actually? Okay? From the lower limit A to B. And this dx, okay? Dx, you can call it, some people call it, this is element of integration. Element of integration. Okay? Now what is the interpretation of this? Since this is equal to this limit, so whatever is the interpretation of this is going to be the interpretation of this. So what is the interpretation of this? The interpretation of this limit is the area of this f of x, area under the curve f of x actually. So this is the area under the curve. So definite integral is basically the area under the curve f of x from A to B. So this is what really is the definition of definite integral actually. Okay? Gonna look like difficult. When we're gonna learn so at the moment we are computing it through limits, so it seems a little bit scary actually. But we're gonna learn the technique where calculating such integrals, in other words, such a limit is peanuts actually. You can calculate it like that. Okay. So first, it's good that we should make sense of this, and this is something that was proposed by Newton and Leibniz actually. So let's calculate sum of integrals, but before calculating sum of definite integrals, that is such limits, okay, let's calculate, for example, let me give you a list of sum of important sums actually. Okay, sum of important sums. By the way, I hope you understand this sigma notation. So if I have, for example, 1 square, so I hope that you understand this sigma notation. So I'm summing this f of xi multiplied by dxi, okay, from 1 to n. So what does this mean actually? So if you are okay with the sigma notation, good. If not, I mean, let me say it explicitly. So if I have, so sigma means sum of what? Of a formula. So I can have some formula, say I, that starts from say 1 and goes to up to n. Say for the formula is I square. Okay? The formula is I square. So this is a shortcut way to write an expression. So what is that expression? So 1 is square, so take 1 and substitute it into the formula. Take I equal to 1, substitute it into the formula. So you're going to get 1 square. Then take next, which is 2, and substitute into the formula. So it's going to be the 2 square. So the next is going to be 3 square up to what? Substitute n, so it's going to be the n square actually. So rather than writing this big expression, so this is a shortcut of doing it. So if I say that, okay, now you take the sum that goes from say I equal to 1 to n, and I have a formula I cube. So what does that mean? That take I equal to 1, substitute into the formula, so it's going to be 1 cube. I hope in your pre-calculus course you have dealt with the sums actually. I mean, if not, please let me know. Okay? 1 cube, substitute 2 cube, then next to 3 cube, and so on and so forth, up to n cube. So this is, I can say, this is the sum of the cubes starting from 1 ending at n actually. Okay? Ending at n. Similarly, I can give you, for example, a sum that goes from say I equal to 1 to say 10 actually, and the formula is 2i plus 1. 2i plus 1. So what would be the first term in this sum? So take I equal to 1, substitute it into the formula. So 2 multiplied by 1 plus 1 is really 3. Then take I equal to 2, substitute into the formula. So 2 times 2 plus 1 is 5. Then 3, so 2 times 3 plus 6, 1, yani 7. So on and so forth. I have to go up to 10 actually. So take 10, substitute it into the formula. So 2 times 10 plus 1. So it's going to be 21. So this is a sum that has been written in this shortcut manner actually. So I hope that you really understand it. So for example, if I'm writing a sum that goes from I equal to 1 to n, and I'm saying I have a, and in subscript I have I. A, and in subscript I have I. So how I'm going to write it? Take I equal to 1 and substitute wherever the subscript, wherever the I is actually. So it's going to be A1, okay, then take 2, substitute A2, plus so on and so forth up to what? AN. So that's a shortcut way of writing the sum. For example, I say I have a sum that goes from I equal to 1 to 10, and I have 10 10 and 10 power I and BR. Okay, so this is formula 10 power I BR. So what does this mean? So when I'll expand this sum, so wherever I have I, I'm going to substitute, whenever I have I, I'm going to substitute what do you call 1 starting from 1 and ending up to 10 actually. So the substitute 1 for example, so you're going to get 10 power 1 B1. So wherever I have I substituted 1, 10 power 2 B2. Okay, the last is going to be the upper bound, you need 10 power 10 and B10 actually. So I hope you got what do you call these indices, the algebra of indices actually, because we have to deal for some time with them actually, at least in this section. At least in this section. Okay. Now let me give you, by the way, now what would be the interpretation of this now? So if I have say sum that goes from I equal to 1 to n, f of xi star times delta x. So if I apply the same strategy and expand this, so what would be this? Wherever in the expression you see I, first substitute 1, plus then substitute 2, plus then substitute 3, up to then substitute n. So the first term is going to be f of x1 star times delta x, f of x2 star times delta x plus so on and so forth, f of xn star times delta x. So this is what is going to be the explicit form of the sum actually. Okay, explicit form of the sum. Now, here are some of the important identities that you need actually. So keep them in head. So first of all, if you have a sum that goes from I equal to 1 to say n, and you have I, so what would be the meaning of it? 1 plus 2 plus 3 up to plus n. So this is equal to, I hope you have learned in your pre-calculus courses or even your FSC mathematics that sum of first n natural numbers is n times n plus 1 upon 2. Sum that goes from say I equal to 1 to say n, and I have say I square, okay, and I want to find this sum. So this would be first substitute 1, so it's going to be 1 square, then substitute 2, so it's going to be 2 square, so on and so forth, and the final thing is going to be n square. Okay, n square. So this sum is known to be what do you call n times 2n plus 1 times n plus 1, n times n plus 1 and 2n plus 1. Okay. N times n plus 1 and 2n plus 1 upon 6. What do you mean by that? For example, if you have to compute the sum 1 square plus 10 square plus up to the 11 square. So one way is that, okay, you calculate the squares and then sum them up, take your calculator and do the calculation. The other is use the formula. See that where this n, the last term is n square, so n must be 11. So this means that this sum is going to be 11 times 11 plus 1 times 22 plus 1 divided by 6. So you can simplify. And whatever answer comes is going to be this sum. Okay, so it's a pretty nice shortcut. And then you have a sum. So these are some of the important aside things from what do you call the definite integral. But these will be very helpful. So I equal to 1 to n, so cubes actually. So for example, if I have a cube, so in other words 1 cube plus 2 cube plus up to n cube is really the same above formula, n times n plus 1 upon 2, but it's a square actually. Okay, this is what is really the three important basic identities. Okay? What is the next thing? The next thing is to tell you some of the properties of the sum actually. Okay? Some of the properties of sum. For example, here are some properties. Properties of this sigma. So first is that if you want to sum I equal to 1 to n, say for example something in which there is no index involved actually. So there is no I in it. So what do you mean by that? The meaning of this is that you are taking this number and summing this up n times. In other words, you are taking this number and summing it again and again and again from one time to n times. In other words, n times. So in other words, this is C plus C plus C, so on and so forth, plus C, how many times? N times. So if you add a number n times, what you're going to get? So you're going to get NC. You're going to get NC. Okay? So if I give you, for example, a number I that goes from 1 to say 100, and I say write 5, so what does this mean? So I am summing 500 times actually. So this is going to be 5 multiplied by 100 because you are summing 500 times. Okay? You are summing 500 times. So this is the first property of the sum. The second property of the sum is that if you have, for example, I equal to 1 to n, a sum C multiplied by AI. So I have a something that involves index but multiplied with a constant C. So if you expand it, how does it going to look like? So this is going to be CA1 plus CA2 plus so on and so forth CAN. Okay, this is what that you're going to get. And now, so C is like, common in all, so you can pull it out. So you're going to have C times A1 plus A2 plus so on and so forth AN. So if I wish, I can write this C as C, the sum that goes from 1 to n, and what do you call AI. So the net conclusion is that if you have a sum that goes from I equal to 1 to n, C is some constant is multiplied with something that has index. What you can do, you can pull that constant out of the sum I equal to 1 to n by distributive law. Okay, so it is like you are taking the common C out of all the terms. Okay. The next important thing is that what if you have two terms which are added with each other and they are in sum. So I have, for example, what do you say? A sum that goes from I equal to 1 to n, AI plus BI. So you have two terms. So what do you mean by that? So I have the sum, so first substitute 1 and 1, so A1 plus B1 into A2 plus B2 plus so on and so forth plus AN plus BN. So this is what that you're going to get. Now I know that this is simply a sum of numbers actually. So if I wish, I can put these A's together and sum them up, and I can put these B's together and sum them up. So in other words, by associative law, this is going to be A1 plus A2 plus, what do you call it, AN plus, so put all A's together, there's nothing wrong in it. Okay? So by just adding them together is not going to change the sum, so B1 plus b2 plus bn. So you're going to get sum that starts from I equal to 1 to n ai plus sum that starts from I equal to 1 to n bi, and you have a sum that goes from I equal to 1 to n ai plus bi. So how to read it? So if you have a sum over the sum of two things, then apply this sum individually, separately. So apply the sum to the first term first and the second term afterwards. So you can apply them, operate, and then calculate the sum. So this would be equal to this sum. And same is the case for the differences. Same is the case for difference, that if you have a difference of 2, then you're going to have a difference here. So you're going to have a difference here. So understanding the summation notation is important. I'm assuming that you know a little bit of it. I mean, if not, please do discuss this in Zoom session. Now let's use these identities, these properties and these identities to calculate some sum set. For example, I want to calculate what is the sum that goes from I equal to 1 to 10 to I, say 2i. Okay, so let's calculate the first 2i. So let's calculate another sum that goes from I equal to 1 to 10, say 5i plus 2. Okay, and another sum that I would like to calculate is say sum that goes from I equal to 1 to n, say 1 to say 100, I plus 1 square, and so on and so forth. Okay, so let's calculate this. So what would be the first sum? I that goes from 1 to 10 and 2i. So if you compare it with, what do you call, these four properties, which properties it matches actually? So it matches with this property. So that I have a constant that is multiplied with something that has an index. Constant multiplied with something that has index. So what you can do, you can pull this index out, pull this number out actually. So it's going to be I equal to 1 to 10 and I. And don't forget that what was the sum that goes from say I equal to 1 to n I. So it was n times n plus 1 upon 2. This was the sum. What was it for a square? I equal to 1 to n I square, for example. So it was n times n plus 1 times 2n plus 1 divided by 6. So by this formula, I'm summing the I from 1 to 10. So by definition, this is going to be 2 times, so in other words, it ends at n, starts from 1, must start from 1 and end at n. So it's n, this n times n plus 1 upon 2. So it's going to be what? So it's going to be 2 of the 10 times 10 plus 1 upon 2. Okay? So if you simplify this, you're going to get 11 times 10, so it's going to be 110 actually. So this is what the sum is. This is what this sum is. What would be, for example, the second sum that starts from I equal to 1 to say 10, and I have 5i plus 2. So first I will apply the property that if I have a sum, sigma of sums, then I can apply this sums separately. So I can say that this is going to be a sum that goes from say I equal to 1 to 10, 5i plus the sum that goes from I equal to 1 to 10, okay, and 2. Okay. Now, which properties must I apply? Okay. Which properties I must apply? Property that previously was I equal to 1 to n. C times of I equal to 1 to n. So this is going to be n's. Okay. Now this first sum is like this sum. So in this I can pull out my 5. So this is going to be 5, and I have a sum that starts from I, that is on I, that goes from 1 to 10, plus